Hello, welcome back to our course on software engineering. We're making some good progress here. And what we have is, this will be the last lecture in this first major section. And we covered a lot of ground as we're moving forward, getting this introduction to the various aspects of software engineering. And so what we're going to be talking about today is software evolution. How do things change over time and how do we deal with that? So the three main topics will be the evolution processes, dealing with legacy systems, and then finally software maintenance. Software change is inevitable. There can be new requirements that typically can happen. The market itself changes. You get more things from your customer. The business environment changes. Errors are reported. You have new computers or equipment that is added, and the performance or reliability of the system may have to be improved. So a key problem for all organizations is implementing and managing change to their existing software systems. So the importance of evolution is organizations have huge investments in their software systems. They are critical business assets. To maintain the value of these assets to the business, there must be changes. They must be changed and updated. The majority of the software budget in large companies is devoted to changing and evolving existing software rather than developing new software. So here is just an example of a spiral mode of development and evolution. So you can be beginning with release 1. You go through the specification, implementation, validation, and operation. And then as you go around that whole circle, you then come back and start that again with release 2 and release 3. So you can also have evolution and services. You can have the development, the evolution, the servicing, and retirement. When you get a point to when you fully retire maybe a product and then you start with something new that is goes beyond the scope of what was originally envisioned, and so that could be a possibility. So in terms of evolution and servicing, the first of all, the evolution is the stage in the software system's life cycle where it is in operational use and evolving as new requirements are proposed and implemented to the system. Servicing is at the stage when the software remains useful, but only the changes made are those required to keep it operational. That is, bug changes, fixes to reflect changes in the software's environment. No new functionality is added. And finally, the phase out is that the software may still be used, but no further changes are made to it. So that may be something useful to consider with the software that you're using as well as the software you're developing. For software processes, the software evolution process depends on the type of the software being maintained, the development processes used, and the skills and experience of the people involved. Proposals for changes are the driver for system evolution. Should be linked with components that are affected by the change, thus allowing the cost and impact of the change to be estimated. Change identification and evolution continues throughout the system lifetime. So in terms of the change identification and evolution process, you can have a new system going to change identification. You propose changes, and then you have the software evolution process that you try to assimilate that and go from there. So the software evolution process has various number of stages here. So you can have a request change, you analyze the impact, you do the release planning, you then look at the implementation and system release. In terms of the release planning, you have to do fault repair, platform adaptation, and system enhancements. And there are some circular things here that you change in the implementation and you see if that is going to go with that next release, and so you strategically plan for what's going to go in each release. For change implementation, you go from the proposed changes to requirement analysis, you iterate through that, then move into the requirements updating, and finally do the software development. For change implementation, iteration of the development process, it's the iteration of the development process where the revisions to the system are designed, implemented, and tested. The critical difference is that the first stage of change implementation may involve programs understanding, especially if the original system developers are not responsible for the change implementation. During the program understanding phase, you have to understand how the program is structured, how it is delivered functionally, and how the proposed changes might affect the program. For urgent change requests, urgent changes may have to be implemented without going through all the stages in the software engineering process. If a serious system fault has to be repaired to allow normal operation to continue, or you can have change in the system's operating environment, say there's an operating system upgrade that has unexpected impacts. And finally, if there are business changes that require a very rapid response, like the release of a competing product. So you want to have an emergency repair process laid out. And so that could be, you have a change request, you analyze the source code, you modify the source code, and you deliver the system, the modified system, and get that out as soon as possible. In terms of agile methods in evolution, agile methods are based on incremental development. So the transition from development to evolution is a seamless one. The evolution is simply a continuation of the development process based on frequent system releases. Automated regression testing is particularly valuable when changes are made to a system. Finally, changes may be expressed as additional user stories. What about handover problems, where the development teams have used an agile approach, but the evolution team is unfamiliar with agile methods and prefer a plan-based approach? Then the evolution team may expect detailed documentation to support evolution, and this is not produced in the agile processes. Where a plan-based approach has been used for development, but the evolutionary team prefers to use agile methods, the agile team may have to start from scratch developing automated tests, and the code in the system may not have been refactored and simplified as it is expected in agile development. So there can be a little bit of some tension in those regards. Let's move on to considering legacy systems. Legacy systems are older systems that rely on languages and technologies that are no longer used for new system development. Legacy software may be dependent on old hardware, such as a mainframe computer, and may have associated legacy processes and procedures. Legacy systems are not just software systems, but are broader socio-technical systems that include hardware, software, libraries, and other supporting software and business processes. So you can have the various elements of a legacy system. You can be thinking about the support software, the application software, the business and policies. And so with that, you have to be considering what is the system hardware that's required, what is the application data and the way that it needs to be laid out, and what are the business processes that are part of that. So for legacy system components, you have the system hardware, the support software, the application software, and the application data. So for the system hardware, the legacy system may have to be written for hardware that is no longer available. For the support software, the legacy system may rely on a range of support software which may be obsolete or unsupported. For the application software, the application system that provides the business services is usually made up of a number of application programs. Finally, the application data, these are data that are processed by the application system. They may be inconsistent, duplicative, or held at in different databases. There's also business processes in the various forms. And so the business processes are processes that are used in the business to achieve some business objective. The business processes may be designed around a legacy system and constrained by the functionality that it provides. And in terms of business policies and rules, these are definitions of how the business should be carried out and constraints on the business. Use of the legacy application system may be embedded in these policies and rules. So here's the layers of a legacy system. You can have the hardware, platform, infrastructure, and software, the application layer, and the business processes, and all of this feeds into a social technical system that the way when it was developed, it was at that time, it was reflecting the understanding of the business, available hardware and software. What if you need to do a legacy system replacement? The legacy system replacement is risky and expensive, so businesses continue to use these systems. System replacement is risky for a number of reasons: lack of complete system specification, tight integration of system and business processes, undocumented businesses rules implemented in the legacy system, and new software development may be late and or over budget. So these are all things that would have to be considered. Legacy systems are expensive to change for a number of reasons: no consistent programming style, use of obsolete programming languages, few people available with these language skills, inadequate system documentation, system structure degradation, program optimizations may make them hard to understand, and data errors and duplications and inconsistency. Organizations that rely on legacy system must choose a strategy for evolving the system. You could scrap the system completely and modify business processes so it is no longer required. You could continue maintaining the system. You could transfer the system by re-engineering to improve its maintainability, or replace the system with a new system. The strategy chosen should depend on the system quality and the business value. There is a lot of move towards virtualization, so perhaps you might be able to contain the legacy system in a virtual environment and still run effectively that way. So here's an example of a legacy system assessment where you're looking at the system quality versus the business value. And so you can see these different possibilities where you might be arguing where this particular entity lies and what you want to be doing about that. So in terms of legacy system categories, a low quality and low business value, these systems should be scrapped. So that's easy to make a decision. For low quality, high business value, these make an important business contribution but are expensive to maintain. It should be re-engineered or replaced in a suitable system if a suitable system is available. For high quality, low business value, we want to replace with commercial off the shelf, scrap and you can scrap it completely or maintain. And for high quality, high business value, you want to continue an operation using normal system maintenance. For business value assessment should take different viewpoints into account. System end users, business customers, line managers, IT managers, and senior managers. You want to be interviewing the different stakeholders and collect the results. So in terms of the issues in business value assessment, you need to be thinking about the use of the system, the business processes, the system dependencies, and the system outputs. If the systems are only used occasionally or by a small number of people, they may have a low business value. The business processes that are supported, a system may have a low business value if it forces the use of inefficient business processes. For system dependencies, if a system is not dependable and the problems directly affect business customers, the system has a low business value. And finally, the system output, if the business depends on system outputs, and the system has a high business value. So for system quality assessments, for business processes assessment, how well does a business process support the current goals of the business? For the environmental assessment, you would want to be asking how effective is the system's environment, how expensive is it to maintain? And finally, for the application assessment, what is the quality of the application software system? If you use a viewpoint-oriented approach and seek answers from the stakeholders, you could be considering these questions. Is there a defined process model, and is it followed? Do different parts of the organization use different processes for the same function? How has a process been adapted? What are the relationships with other business processes, and are they necessary? And finally, is there a process effectively supported by the legacy application software? So for an example would be looking at a travel ordering system may have a low business value because of the widespread use of web-based ordering. In terms of factors used in environmental assessments, you can be thinking of the supplier stability, the failure rate, the age, and the performance, and keeping all of those in mind. There's also the support requirements, the maintenance costs, and the interoperability. So we have like a variety of different factors to consider. In terms of factors used in application assessment, continuing on, you want to be considering the understandability, the documentation, the data that's being used in performance, and what is the programming language, configuration management, test data, and personnel skills. Those also could impact whether you want to be maintaining that application or not. So for system measurement, you may collect a quantitative data to make an assessment of the quality of the application system. The number of system change requests, the higher the accumulated value, the lower the quality of the system. The number of different users interfaces used by the system. The more interfaces, the more likely it is that there will be inconsistencies and redundancies in these interfaces. The volume of data used by the system. As the volume of data processed by the system increases, so too does the inconsistency and errors in that data. Cleaning up old data is a very expensive and time-consuming process. So let's get into software maintenance. Modifying a program after it has been put to use is what we're talking about here. The term is mostly used to change the customer software, changing custom software. Generic software products are said to evolve to create new versions. Maintenance does not normally involve major changes to the system's architecture. Changes are implemented by modifying existing components and adding new components to the system. So the types of maintenance that could take place is fault repairs, environmental adaptation, and functional addition and modification. Fault repairs can deal with changing a system to fix bugs and vulnerabilities or correct deficiencies. Environmental adaptation could mean adapting the software to a different operating environment, changing the system so it operates in a different environment from its initial implementation. And for functionality, this would be modifying the system to satisfy new requirements. So here is a perspective. You can be thinking about the maintenance effort distribution. The functionality addition is, on the order of 60%. Fault repairs is maybe a quarter, and environment adaptation is a little bit less, on the order of 19. So in terms of maintenance costs, usually it's greater than development costs, 2 times to 100 times, depending on the application. It affects by both technical and non-technical factors. It increases as software is maintained. Maintenance corrupts the software structure, so making further maintenance more difficult. And aging software can have high support cost for a number of factors, including if it's an old language or compiler, something like that. It's usually more expensive to add a few new features to a system during the maintenance than it is to add the same features during the development. A new team has to understand the program being maintained. Separate maintenance and development means there is no incentive for the development team to write maintenance software. Program maintenance work is unpopular. Maintenance staff are often unexperienced and have limited domain knowledge. And as programs age, their structure degrades and they become harder to change. So maintenance prediction is concerned with assessing which parts of the system may cause problems and have high maintenance costs. Change acceptance depends on the maintainability of the components and affected by the change, and implementing changes degrades a system and reduces its maintainability. Maintenance costs depend on the number of changes, and costs of the change depends on maintainability. So here are the different aspects of the maintenance prediction in terms of predicting maintainability. What parts of the system would be the most expensive to maintain? In terms of predicting maintenance costs, you would be thinking about what will be the lifetime maintenance cost of the system and will be the cost of maintaining the system over the next year. And then for predicting system changes, you would be thinking about what parts of the system are most likely to be affected by change requests and how many change requests requests can be expected. So for change prediction, this is predicting the number of changes required and understanding the relationships between a system and its environment. Tightly coupled systems require changes whenever the environment has changed, and factors influencing the relationship are the number and complexity of system interfaces, the number of inherent volatile system requirements, and the business processes where the system is used. For complexity metrics, the predictions of maintainability can be made by assessing the complexity of the system components. Studies have shown that the most maintenance efforts is spent on a relatively small number of system components. The complexity depends on the complexity of control structures, of the data structures, and of the object methods and module size. For process metrics, the process metrics may be used to assess maintainability, the number of requests for corrective maintenance, the average time request for impact analysis, the average time taken to implement a change request, and the number of outstanding change requests. If any or all of these is increased, this may indicate a decline in maintainability. For software re-engineering, restructuring or rewriting part of a legacy system without changing its functionality, this can be applicable when some, but not all the system of a larger system require frequent maintenance, and re-engineering involves the adding effort to make them easier to maintain. The system may be restructured and redocumented. So what are the advantages of re-engineering? There is a reduced risk. There is a high risk in new software development. There may be development problems, staffing problems, and specification problems. In terms of reduced costs, the cost of re-engineering is often significantly less than the cost of developing new software. So here is an illustration of the re-engineering process. And so you can go from the original program, you do the source code translation, and you either do reverse engineering or program structured improvement. And so you think about which is necessary. You can do program modularization, data re-engineering, and so forth. So the re-engineering process activities, as we were trying to show in the figure, you have the source code translation, the reverse engineering, program structure improvement, program modularization, and data re-engineering. So these are all the things that you need to be considering in that re-engineering process. In terms of the approaches, there is a range of increasing costs. And so the lowest cost would be automated source code conversion. That would be great if that can work. A little bit higher is automated program restructuring. A little higher, automated restructuring with manual changes, programming and data restructuring. And finally, the highest cost would be restructuring plus architectural changes. So for re-engineering cost factors, the quality of the software to be engineered, that needs to be considered, the tool support available, the extent of the data conversion, and the availability of expert staff for re-engineering. For refactoring, the refactoring is a process of making improvements to the program to slow down degradation through change. You can think of refactoring as a preventative maintenance that reduces the problem of future change. Refactoring involves modifying a program to improve its structure, reduce its complexity, or make it easier to understand. And you refactor a program, you should not add functionality, but rather concentrate on program improvement. Re-engineering takes place after a system has been maintained for some time and maintenance costs are increasing. You use automated tools to process and re-engineer a legacy system to create a new system that is more maintainable. Refactoring is a continuous process of improvement throughout the development and evolution process. It's intended to avoid the structure and code degradation that increases the cost and difficulties of maintaining the system. So what are, quote, bad smells in program code? You can have, is there duplicate code? Are there long methods? And are there switch case statements? These are things that can be problematic that you would want to be thinking about. Is the same code, a very similar code used in different places of the program? This can be improved and implemented as a single method. or long methods is a program. If a method is too long, it should be redesigned as a number of shorter methods. And finally, for switch cases, these often involve duplication where the switch depends on the type of value. The switch statement may be scattered around a program. In object-oriented language, you can often use polymorphism to achieve the same thing. Data clumping occurs when the same group of data items reoccurs in several places in the program. These often can be replaced with an object that encapsulates all of the data. In terms of speculative generality, this occurs when developers use generality in a program in a case it is required in the future. This can often simply be removed. So for some key points in this chapter, software development evolution can be thought of as an integrated, iterative process that can be represented using a spiral mode. For custom systems, the cost of software maintenance usually exceeds the software development costs. The process of software evolution is driven by a request for change and includes change impact analysis, release planning, and change implementation. Legacy systems are older systems developed using obsolete software and hardware technologies that remain useful for a business. It is often cheaper and less risky to maintain a legacy system than to develop a replacement system using modern technology. The business value of a legacy system and the quality of the application should be assessed to help decide if the system should be replaced, transformed, or maintained. There are three types of software maintenance, namely bug fixing, modifying software to work in a new environment, and implementing new or changed requirements. And finally, software re-engineering is concerned with restructuring and redocumenting software to make it easier to understand and change. Refactoring, making program changes that preserve functionality is a form of preventative maintenance. All right, well, thank you very much. We've made it through the introduction to software engineering sections, and with that, we'll end the lecture for now. Bye-bye.